Before I do anything else, I do want to mention for assignments, you're going to want to go ahead and especially if you're in Smart Start, go to Wiley course resources on the Canvas page and make sure you're signed into Wiley because it should have that nice kind of pass through thing where you don't have to have a code, things just work, but they only just work if you're signed in, and they only just continue to work if you have signed in before the opt-out date for Smart Start. If you're not in Smart Start, I'd still recommend it, like going to Wiley course resources and signing in before the 26th, just to make sure nothing goes weird after that date as it transitions to figuring out who is and is not in Smart Start. I don't know exactly how that happens on the back end, but I just want to make sure no one gets locked out unexpectedly because of something like that, because it'll take a little bit of a turnaround to get that fixed up with the Wiley rep. So by the end of today, please go to Wiley Course Resources, make sure you're signed into Wiley, and then go back to Canvas, check that you can access the pre-lecture videos, because I put that up. They're not due for like 2 weeks, but just so you know that you can get in, so we can fix any issues with that early on. Last class, I asked about that thing with the rolling can. So I'll replay that so we all know what we're talking about here, and then I'm going to ask if anyone thought of an explanation for that. I now have a piece of wool, a PVC pipe, which is chemically similar to vinyl. I'm going to rub them together until the PVC is charged up. I've got an aluminum can here. I'm not going to touch the can. I've not done anything to charge it up. I've not rubbed anything on it. But if I hold the PVC near it, you can see that the can is attracted by the PVC pipe. So if I've never charged the can, how is it being attracted by the PVC? Okay, so the can is electrically neutral, has an equal number of protons and electrons. The PVC is charged negatively, so it has more electrons than protons because it was rubbed on the wool. So the wool lost electrons and they were transferred over to the PVC. But what's going on with the can? How is it attracted to the PVC?
Because it has equal amounts of positive and negative charges. So the positives are closer to the outside, and so they're basically um, the negative charges on the PVC pipe are basically pulling the negative charges away from the outside of the can more away from the can. Thus, so you have an interaction between the positive and the negative. Uh, and in particular, the negative is coming from the pipe.
Yeah, yeah. And Suleiman, do you have anything to add to that?
Yeah, I was just gonna say that the PVC pipe, when it's electrically charged, it brings the positive charges from the can closer to it. So it's what's it called? It's charged by induction. So when the charges attract, they pull towards each other.
Okay. Yeah, that is close. Like mo most of that was correct. The one thing I'll correct on is that the positive charges did not get any closer because they can't move. They're the things that stay fixed, but the electrons do. So let's see. I'll just draw it in tiny here because I got more things I got to do down below. So we had that negatively charged PVC. The can originally had equal numbers of positive and negative charge, all kind of sitting pretty much uniformly throughout the surface of the can. So none were any closer to or farther away from the PVC until we brought the PVC up near the can. At that point, the electrons in the can were repelled to the opposite side. Because the can is a conductor, the electrons are free to move along its surface and through its volume as well. I'm not saying the empty volume within the can, but as far as like the material, the aluminum. So those were repelled. Leaving some positive charge over here without those electrons. So the net charge of the can is still 0, but it's just kind of polarized. That's the term we use. The charges have moved to opposite sides. And these positive charges are attracted. Okay, so when I say positive charges don't move, the can still roll, so they move in that sense, but don't move atomically. They don't move within the structure of the aluminum. Uh, but we've got attraction and repulsion. Why does attraction win out? Because the can rolled towards the PVC. It was not repelled, and it did not just sit there because of a balancing of attraction and repulsion. So why does attraction win?
Is it something like because the can started moving, so it's easier to keep it moving rather than to stop it?
That would still hinge on that the direction it started moving was towards the PVC, which still comes back to this question. So not quite.
Because the positive and the negative charges are closer to one another.
Yes, yeah, that's exactly it. So because the electrons in the can were kind of sent off to the other side, the remaining positive charges are sitting closer and they don't move anywhere else. They stay fixed in place. And so you don't worry about them also going elsewhere in the aluminum. So that attractive force ends up being larger than the repulsive force. And that's why the can then rolls towards the PVC. So that is called induction because it is charging without any direct contact with the, in this case, can. It's also different because what happens when we take the PVC away from the can? What happens to the charges in the can?
I'm pretty sure it balances out.
Yeah,
Yeah,
things
they go
just
back to the original spot.
they return back to normal. It redistributes itself in this electrically neutral way, partly because that minimizes the energy associated with that system. That's another principle of physics, but things return back to more or less the way they were before. Exactly right. So we're seeing here the difference between charging by contact and by induction. With contact charging, which is like friction charging, it just takes a little bit less effort with conductors. Some of the negative charge off something just transfers to the conductor. And so you end up with negative charge on the conductor. Not too interesting. It does spread over the surface of the conductor. That's a fact we'll come up with later, we'll prove later. But induction, what happens is what we just saw with the can. The electrons are, if you bring something negative up to it, repelled. If you brought something positive, they'd be attracted. In either case, the net effect is an attractive force towards the charged object. But the electrons get repelled. But that repulsion is weaker than the attraction of the positive charge that's left over. I have no idea why I just wrote over everything like that. Hold on. It's like a cat when you're using a computer. It just wants to write all over, step all over the keys. Okay, so that's what we saw with the can. I'm going to bring up another video, another example of induction. And where'd it go? 2020. And this slightly extends on that concept. So I'll ask you what happens here. I'm going to show you another example of induction here. I'm going to charge up my PVC as usual. I'm going to hold it near, but not touching, this spherical conductor. And I'm going to bring it back away. If I touch the conductor to my electroscope, nothing happens. the conductor is not charged. Nothing too surprising there. But if I now charge my PVC up again, hold it near but not touching my conductor, but tap the conductor with my finger. When I hold it up to my electroscope now, you can see that the conductor is charged. My electroscope leaves completely spread apart. So how did I get charge onto that conductor? What did touching it with my finger do? Okay, so what's the answer to that?
By you touching the PVC pipe after you charged it, it charged you as well. So when you touch the electroscope, it basically um those that negative charge was charged onto the electroscope, or the positive was charged onto you onto the electroscope, which is why it showed that there was some type of charge interaction.
Okay, I think that's a really good guess, and that may even happen to an extent. But two disputes to it. The first is I was holding the PVC by one end, and since it's an insulator, that charge that was developed on its surface would not be where my hand was that was holding it. And that wasn't the hand that touched, if I remember right. Oh, that was the one holding the wool. So that could have happened to an extent. But the other objection still stands. The other thing is that if I had brought up anything else, that still would have worked. If I had brought up any other conductor, at least. So if I had brought in something I had never touched that was metal and tapped it on that sphere, this same thing would still happen. So do you want to revise any?
Then would it just be the fact that you're touching the metal, which is a conductor? It's basically transferring electrons to your hand, I mean
Yes. Yeah.
finger, and then you're touching the electroscope.
Yeah. Yeah, that's exactly it. So, well, I'm not touching the electroscope, but the conductor, the sphere is, yeah. So where we were left at with that induced charge was that we've got positive over here, negative on this side. When I tap it, some of that negative charge is sapped off onto me, and some spreads over the surface of my body, some even may make it to the ground. Okay, so the negative charge, some of it flows off until there's what's called, you reach the same potential as this thing. We'll get to what that means later. But to do that, some of this negative charge leaks off through me. And what we're left with is a net positive charge. Okay, so that positive charge is what's showing up on the electroscope. Some of it is transferred to the bulb of the scope, and then you get the leaves repelling because of that. So that's how you can end up with an actual permanent net charge from induction. You do need contact to do that, but it's still an inductive process up until that point. Okay, any questions on that? Okay, I have two more induction things because it's an interesting kind of property. I don't know why I keep closing completely out of this. The first is that we've been looking at conductors so far. So I'm going to show you this with an insulator. Induction can also occur with insulators like paper. So if I charge up my PVC with my wool again and hold it near the paper, you'll see bits of paper jump to the PVC pipe. unlike with conductors, electrons can't easily move in insulators. So they can't move to the other side like in a can to have a net attractive force towards the PVC. So if they're not able to move freely through the paper, how is induction still happening? Okay, what do we think on that? Have you stumped on that one? It is tricky.
Yeah, I don't get that one.
Okay. So I'll explain it because this one is very subtle, not even just in the description of it, but physically it is a very subtle thing. We have to go to the atomic level of this. So we've got our nucleus, whatever kind of molecular structure we've got going on into paper. I'm going to simplify down because I'm a dumb physicist, not a chemist. But we've got our electrons orbiting, and they're not really orbiting. We all know it's the electron cloud probability distribution thing, but that's just going to be easier to explain this. Okay, so they're doing their thing in different orbits. Right. When I hold up that negatively charged PVC, those electrons don't leave this nucleus like they can in a conductor, but they do spend just a little bit more time on the side of the nucleus that's farther away from the PVC. So, right, the scales on this are all sorts of wrong, but if I hold up my conductor to my paper, this is what's happening in each little atom, each molecule of the paper, is the electrons within it are spending just a little bit more of their time on this side. Okay, and I'm not even getting the number of electrons correct here for my filled orbitals, but you know, dumb physicist. Okay, so the orbit gets kind of stretched out into an oblong sort of shape, and that ends up with the same effect as this large scale induction that happens with conductors. You have a net positive charge due to the protons in the nucleus on one side and a net negative charge on average on the opposite side. And you still get the same inductive effect. Okay. Does that make sense?
Yes.
Okay. Like I said, very subtle, atomic level stuff, but it is the same sort of process on a just much smaller scale. Okay, and one more. There's nothing new. There's no puzzle in this one. I just think it's a neat thing. And I closed the videos again. Wow, I'm just out to get myself today. Okay, so one more induction example that's just kind of neat. Okay, this is a variant on that last induction demo. I'm going to charge up my PVC. I'm going to hold it near now two spherical conductors that are touching each other. And y'all can hear this, right? I'm going to scoot one away.
Yes.
Okay, good.
Yes.
And now, without even using my hands to touch the conductors, I have a charge on one. So the leaves have spread apart. If I now touch the other one to it, the leaves get a little bit closer together. So what happened here is... Does anyone want to take a guess at what happened before I explain it in the video?
Can I try?
Yeah.
So you charge your PVC pipe,
Mhm.
and then you set it to a little bit. So when you went to set it down, could some of those electrons actually transfer from the pipe to the sphere. But then you separated the two spheres.
Let
So
me
it,
let me stop before you get too close because I'm guessing the rest of this will be correct, but I didn't transfer any electrons from the pipe to the sphere because they never touched.
okay.
Yeah, so that part. See if you can revise on that a little bit.
So would it just be the simple fact that you had two conductors together? Um, and basically what that did is create basically a media where you had the negatives kind of on the outside, where the protons, of course, they stay where they're at. So when you touched the two charged portions, it had um, so you touched it first with the side I would presume, if this is correct, would be the positive portion of the sphere because you had them in contact, and then you touch the other side of the sphere with what I would presume would be the negative side since they were in contact. So that the so it kind of slowly closed them up because it was closer to neutrality basically.
Yeah, I agree with that part. That part is all fine. I think the conflict is maybe still just with the first bit of how we ended up with charge on my two spheres. Because if we think back to like the can example, um, I held my PVC up to the can and we separated charge, but things went right back to the way they were when I took the PVC away. In this case, when I took the PVC away, I still somehow had charge on my two spheres. So it's just the question of how did I end up with that charge? But I'll let this play and I think it'll cover it. And you got at least 80% of the way there. It's just that first little bit. So you did really good. This is just I've added so many layers to this on top of what we started with that I think it's just getting a little bit confusing in its own nature. All right. Initially, my conductors were uncharged, and I held up my negatively charged PVC pipe that's going to repel the electrons in both conductors off to the other side, a lot like in the aluminum can. So we have an excess of electrons over here, a deficiency of electrons over here. When I push the two apart then, those electrons that had gotten pushed over here can't return to the first conductor. And so this conductor becomes negatively charged, while this one is positively charged because it's missing those electrons that move to this one. So when I touch one to my electroscope, the electroscope leaves pulling apart because it's charged. But when I touch the other to it, this other one is oppositely charged from the first one. And so it's going to make the leaves come closer together because it's neutralizing some of that charge that was sitting on the electroscope. Okay, so was it just that first part that was a little bit different than you were thinking?
Yes, definitely.
Okay, yeah, so
But
you did great. All right. Any questions on that, anyone? Okay, so we've been talking about the fun qualitative properties of electricity for a while now. Now it's time to get into the not as fun math part, actually quantitatively describing electricity. And so we want to turn some of these observations we've made into things that we can use to predict other stuff through calculations. And this is where, everyone gets sad and it's not the fun class it started as, but this is the physics as well. All right. So we'll start with the things we do know just from our observations. We simplify to the idea of a point charge is the first thing. This is important. So point charge means just a concentration of charge, just a little dot of charge. It could mean individual protons or individual electrons, but it could also actually mean much larger things like that spherical conductor. if you're considering it at a distance very far away from the conductor. It is literally the same as how if you're standing really far away from that conductor, it looks like a tiny point in your vision. So through the scale of things, how far away you are from your charge distribution, pretty much everything eventually looks like a point charge at a far enough distance away. There's some exceptions to that, but that's the idea. So this isn't restricting us to just protons, but it is restricting us to anything that behaves like a point charge. So just to make that clear. All right, so for unlike charges, what do they do?
Attract.
They attract.
Yeah. So I'm going to draw a line between my two charges because that's the direction. You might call it the line of action of the force. So the proton will be attracted towards the electron. The electron will also be attracted towards the proton. Call that negative F. How do those forces compare to each other? The force the proton feels versus the force the electron feels.
Equal and opposite.
Why?
I'm not sure.
Okay. Think back to physics
Are,
1.
are we assuming that they're neutral?
So no positive charge on one side, negative charge on the other.
Because it's a +1 and a -1 charge.
Okay. This would still be true if I had a +1 and a -2.
It's like Newton's, one of his laws. I'm not sure which one.
That's it. Newton's third law. So that's not really, to be fair, an explanation because, okay, what's the explanation for Newton's law? But it is still a property of charged objects that Newton's third law holds. And that law is that for every force that object A exerts on object B exerts an equal and opposite force on object A. So Newton's laws still apply to charged objects. All three of them do. And that means that pretty much nothing we learned in physics 1 is gone. It's all still fair game. So that's the next part that's a little bit of a letdown. We're not done with physics 1. We still got plenty to say from it, but applying it to charged objects. Okay, that was very long-winded. Let me speed up a little bit now. So we're going to start quantifying some things. So we add some variable names to describe, for instance, the distance between these. I'll call that R. I'll do the same for my like charges, which I know repel. And they're going to repel along the line joining them. Call that plus F and minus F. And that's still R. So these ones attract, these ones repel. And have I missed anything in chat? No, okay. All right. So now let's do the quantitative bit. How large is this force? That is described by what's called Coulomb's law. It says the size of this force. So direction we've already accounted for, and that is how we approach problems like this. Once we account for direction, we do absolute values of stuff so we don't double count negatives for things. You'll see what I mean when we do a couple examples. So that's the size of the force. It depends on how large your two charges are. So this is the size or magnitude of charge 1. Measured in coulombs. And same here for charge 2. Also measured in coulombs. And the closer you get, the larger this force becomes, the closer the two charges get to each other. So I should have R in the denominator so that the smaller R is, the larger the force is. Also, through experiment, you can determine that it goes as r squared, so it's an even more powerful dependence on distance than we thought. But to get things to work out correctly, we have to introduce this constant k out front. That just says if I have charge q1 being some certain value, charge q2 being a known value, distance being a known value, I can measure the force. It turns out to not be exactly equal to q1, q2 over r squared, but it is proportional to it. To get exact equality, to get the correct force predicted, I just add that constant k out front to fix things up and get the right number. So that's called Coulomb's constant. And it is equal to 8.99 times 10 to the 9th. The units are just what they have to be for the units of the equation to work out. Newton meter squared per Coulomb squared. And R is the distance between charges measured in meters. But you do square it. Okay, so that is Coulomb's law. The force is equal to K, magnitude of Q1 times magnitude of Q2 over the distance between the two charges squared. The electron charge, we can now finally state, give its value. It is negative, this thing we call the fundamental charge. So that's negative 1.60 times 10 to the negative 19 coulombs. So whatever we defined as a coulomb, we just said the electron charge is this fraction of that unit. Okay, proton charge. It's the same charge, just opposite sign. Same magnitude of charge, I should say. So just positive 1.6, blah, 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 blah. Okay, you'll sometimes see this written, and usually this is going to be written this way when you see it in math. K is sometimes written in terms of this thing called the permittivity of free space. So when I say math, I mean like when we're doing derivations. When we're doing calculations, like example problems, we always use K. So epsilon 0, ooh, I didn't fix this up. I need to fix this right here. Epsilon 0 is equal to 1 over 4 pi times K. And so epsilon 0 equals this number right here. I meant to fix up this number on the right, but I mismatched things between stuff. So epsilon 0 equals 1 over 4 pi K, which equals 8.85, so on and so forth. And so you could also write Coulomb's law as F equals 1 over 4 pi epsilon 0 Q1 Q2 over R squared. That's an alternative way to write it. Okay. Let's find the force between two 1 Coulomb charges. So that is, now that we see the number of electrons, or what fraction of a Coulomb the electron charge is, we can see this is a very large amount of charge. We're dealing with 1 Coulomb, but we're going to put them a kilometer apart, pretty far distance apart from each other. So you got positive and negative 1 Coulomb. And the distance between them is 1 kilometer. And we know since they're oppositely charged, they will attract, but we want to know how large that attractive force is. So someone do this calculation for me, because there's a lot of exponents in this and it's very easy to get one wrong. I also want to see if you remember SI units. If you like, you can round 8.99 to just 9 times 10 to the 9th. That won't really ever steer you wrong.
I got a weird answer. It's 8,990.
That's the correct answer. Nothing weird about it.
Oh.
Except that it is a concerningly large number, right? Is that
Yeah.
what's weird about it? Yeah. Okay. So 8.99 times 10 to the ninth is what K is equal to. Newton meter squared per coulomb squared. Our magnitude is 1 coulomb and 1 coulomb. So you should not put a negative here because we took absolute values of both. That's what I mean about we already accounted for direction. Now that we've done that, forget about signs of charges because it will mess you up on directions of things later. Okay. The other thing that could have tripped you up is that it's kilometers. We need to be in meters. That's SI. So that's 1,000 meters, and we square that. We do get, I'm just rounding pretty aggressively, 9,000 newtons. And that is kind of concerning because that's about 2,000 pounds of force. So if you take these big balls of charge and put them 1,000 meters away from each other, so that's close to a mile, right? 3,000 feet, 2/3 of a mile-ish. You're still going to have a 2,000 pound force of attraction between them. So you don't want to be standing between those two charges if this happened. What that tells us, for one, is that 1 coulomb is a huge amount of charge. In fact, about 6.25 billion, not done, billion electrons worth of charge. So you take 6 billion of them and you take a billion sets of that. That's how many electrons that is. Why is it such a huge unit? Because the actual base unit that we use in electricity is the ampere, a unit of current. In that case, 1 coulomb per second, so a moving amount of charge, is not so crazy. 1 ampere is not a crazy number. But static charge, which is what we're dealing with now, charge just sitting somewhere, 1 coulomb's a crazy amount sitting somewhere. In a lightning strike, about 20 to 30 coulombs of charge are transferred between the ground and the sky, the clouds. So pretty significant charge there. All right. Have you noticed, looking at Coulomb's law, that it looks familiar? Hopefully so.
Is it the gravitational?
Yeah.
Um, the I think it's just the gravitational equation.
Yeah, law of universal gravitation, Newton's law of gravitation, lots of different names. It says that the gravitational force between 2 point masses, 2 concentrations of mass, is proportional to the product of the 2 masses. We don't need absolute value because we don't have negative mass, as far as we know, over the square of the distance between them, and you scale that by a proportionality constant. So the electric force between 2 charged objects and the gravitational force between 2 masses has the exact same form. That is an interesting, as far as we know, coinkydink of science, of nature, that they have these similar behaviors, but inverse square laws in general, meaning ones that have that 1 over r squared dependence, are very common throughout all of physics. So there is that, you'll see that as a trend in physics, 1 over r squared type behaviors. Okay. So we're going to draw a lot of analogies with gravity later because it'll help us understand some things better. How do you think the gravitational force compares to the electric force? Which one's bigger?
Gravity.
Okay. So let's do a calculation and we'll see what happens. We're going to look at a hydrogen atom where we've got 1 proton, 1 electron. Of course, they're going to exert electrical forces on each other that are attractive. They attract each other. You're also going to exert gravitational forces. And I'm going to draw them the same length so that we don't cheat and just base it on that. The electrical force is K times the magnitude of the electron charge times the magnitude of the proton charge over the square of the distance between them. I've not put a distance. It's going to turn out it won't matter, but we could just pretend it's some particular distance, 1 meter if you want, or whatever the orbital radius of that electron is in the hydrogen atom. Okay, gravitational force, G times the mass of the electron times the mass of the proton times the square of the distance between them. That's why it doesn't matter. Whatever the distance is, it's going to cancel out. Okay, so this is K, electron charge, proton charge, over G, electron mass, proton mass. Now this is a disgusting amount of exponents, so I'm not going to make you do this one. K is this number right here. Electron charge, the magnitude of it, so dropping that negative, is this right here. Proton charge is the same in magnitude. G, you may not remember it, but 6.67, so 6, 10 to the negative 11 Newton meter squared per kilogram squared. Mass of the electron, 9.11 times 10 to the negative 31. So that's somewhere up above. And the mass of the proton, 1.67 times 10 to the negative 27 kilograms. All right, I'm going to give you all a second to get caught up on that. It's a lot of numbers. If I were doing sig figs, I should have put a 0 up here, but who cares? Okay, so what I'm calculating here is the ratio of the electric force to the gravitational force. In other words, this will tell me how many times stronger or weaker the electric force is than the gravitational force. So if this number came out to equal 5, that would mean the electric force is 5 times stronger than the gravitational. If it came out to 1/5, it would mean the electric force is 5 times weaker, so on and so forth. What it ends up coming out to is 2.27 times 10 to the 39. So which one's stronger?
Electric.
Electric by an unbelievable amount. I like to really stress this by not using scientific notation. F-elect is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. That many times stronger. Okay. So you ask, why is everything not falling apart from these ridiculous electrical forces? Why am I held on planet Earth by a gravitational force? I hope those are the questions that are coming up. Anyone know the answer?
We have relatively small charges, and usually it's going to even out, like become neutral because we're grounded to the earth.
Okay, let me touch on something in the chat real quick, but yeah, that is pretty much it. Why are we saying electric is stronger again? The answer is that up at the beginning, I'm saying electric divided by gravitational. So you could also look at this as, all right, I multiply both sides by F gravitational. It ends up saying F electric equals 2.27 times 10 to the 39 times F gravitational. So I'm saying the electric force is that many times greater. And that's a number bigger than 1. So that means F electric is larger. But yeah, so the answer is that yes, there are all of these forces at play. So right now in our body, these kinds of forces are acting, but in the net, the overall net force from all of them adds up on average to 0 in most cases. When it is not 0, you have a net charge on something. It is just such a very small amount of charge that's built up that this becomes still not very strong compared to other forces. Okay. We have so much more mass in those materials that we're holding up to each other compared to the amount of net charge we've built up that the gravitational force dominates just sheerly by the amount of extra mass that's available. The same goes with the Earth. It is an enormous amount of mass with a relatively small net charge. And so even though the gravitational force inherently is weak, it's significant because there's a lot of mass to exert it. Hopefully that makes sense. It also means, though, if we did not have neutrality in most of the universe, we didn't have just very small pockets of net charge in different places, everything would either be collapsed in on each other if we had, excess of one type of charge and you have attractive forces, or be torn apart. And that's from repulsion. So either would be no chance of us existing. We're in like the Goldilocks zone of charge, which is 0 net charge. Okay, so that's pretty wild. All right, now let's get back to reality, do a little bit more math with it, freshen up on some things from Physics 1 again. So I think we'll be able to do this example on the left and pick up the one on the right next time. I took too much time trying to be dramatic. But we're going to start adding up forces now. And that's another nice property of electric forces. They do add like any other force. They add as vectors. Okay, so I'm going to call to the right the positive and to the left the negative direction. I'm asked to find the net force on charge Q1. So I need to consider the force charge Q2 exerts on it and charge Q3. Which way will the force charge Q2 exerts be directed? To the left or to the right?
I feel like
To
to
the
the right,
Left.
towards Q3.
Okay. So for charge Q2, it'll be to the left, but for charge Q3, you're correct, it will be to the right. So since Q2 is negatively charged and Q1 is positively charged, Q2 will attract Q1. Q1 also attracts Q2, but that's not what we're being asked about. We're asked about the force on Q1. So I'll label that the force charge 2 exerts on charge 1. And then we said for charge 3, since charge 3 is negative, it will attract charge Q1 as well, but that attractive force would end up being directed to the right. So that's F3 on 1. Okay, we are asked to find the net electric force. So which way will the net electric force point?
To the right. To the right,
Why do you say to the right?
because Q3 has a greater negative charge than Q2.
Perfect. Yeah, the size of the charge. And so the force it exerts, F3 on 1 will be larger than F2 on 1, meaning the net force, the vector sum of those, will be to the right. But we'll be able to see that from the math as well. We just want to check beforehand. Okay, so to check it, we need to calculate F2 on 1 and F3 on 1. So we use Coulomb's law to do that. And I like to also label R now when I'm dealing with multiple charges, so I'll call it R12. That's the distance between charges 1 and charge 2. Just be Coulomb's constant times Q1. You may notice micro coulombs. So we said a coulomb's a huge amount of charge. You don't see that very often. So we start to use micro a lot for talking about charge. Do you remember what the prefix micro means?
10⁻⁶.
Yep. So 3 times 10 to the negative 6. And then for charge Q2, 4 times 10 to the negative 6. Again, ignoring the negative out front. We don't care that it's a negative charge anymore because we already accounted for that with the direction of our force vector. The distance is 0.2 meters. We square that. So that'll come out to 2.7 newtons. F3 on 1, we can also calculate in pretty much the same way. I'm gonna jump past putting the numbers in just because it eats up a little bit of time, but it'll come out to 8.4 newtons when we put those values in. And then the last thing, F net, which you may have seen sigma F for that as well. It's the same thing. I think I used sigma F actually. So I'm going to make this mistake probably. So just to let you know ahead of time, sigma F and F net, same thing. All right. So here is where I can account for the signs, the directions of those forces. F3 on 1 is to the right. So it's positive 8.4 newtons. And then I'm adding forces, but F2 on 1 itself happens to be to the left. So it's negative. And so we will get positive 5.7 newtons. And that positive tells us exactly what we were expecting, that the net force is to the right. Okay. Are there any questions on that? I had to rush it a little bit, so if there are, please let me know.
I have a question for
Yes.
F net. When we put the signs, the plus 8.4, and then there's the negative 2.7. We put those signs because of the direction that they were in.
Yes. Yeah. So it's like in physics 1, we'd look at like a free body diagram, which really I should have drawn, but it would look like this will be F2 on 1 and F3 on 1. And since F3 on 1 is to the right, I would list it as a positive component force. And F2 on 1's to the left, I'd list it as negative. If you did the table that we might have done in physics 1, don't write this over here because I need this space next time for the other example, but you would write it like this. The X component would be negative F2 on 1. There's no Y component. There's no Y component for F3 on 1, but it does have an X component and it's to the right. Does that help?
Yeah, that helps.
Okay.
Okay, I just wanted to make sure because I didn't want to get the signs confused.
Yeah. And I will at points do this table. Sometimes I may not for space reasons and time, but you can always come back to this.